Welcome back to the next session on the unsupervised learning. So, in the previous session we covered the k-means algorithm. Now, in this session we would talk about some of the metrics. We would talk about something called Silhouette score, which is quite a popular metric which is used to measure the quality of the clusters. So, in the first k-means algorithm we understood that how the clusters were formulated, right. So, this is a metric which would be helpful for us to measure the quality of the clusters. So, whether the clusters which have been generated are good quality or not, right. So, it also quantifies that how similar each data point in one cluster is to the data point in its own cluster, which is the cohesion, compared to the nearest neighboring cluster, that is the separation, right. So, these two aspects would be covered over here. So, it can range the value of it, this can range from -1 to +1, with the higher values which would be indicating a better defined clusters, right. So, for each of the data point I, for example, in the data set we would calculate the average distance A, right, between the data point I and all other data points in the same cluster. This is the first step that I am going to do, right. Similarly, I would also calculate the average distance B between the data point I and all the data points in the nearest neighboring cluster, that is the cluster other than its own, right. So, the second step would be that I would calculate this score for the data point I given by, say, suppose Silhouette score would be as you can see in this particular diagram. It would be how it is defined. This is the formula that I have defined, which is the B minus of A. The B and A have been defined in the previous slide, and divided by the max of A comma B. And then obviously I would compute the average score over all the data points to get the overall score for the entire clustering, right. Now, let us see what is the interpretation of this score, what exactly I must know that how to interpret this. If this score is greater than 0, which would indicate that the data points in the cluster are closer to each other than to the neighboring cluster. So, in a way we need higher values indicate a better clustering, right. It can be the score could be 0 also. So, in that case it suggests that the data points are on the border of the two clusters. So, obviously I would not like to have this kind of scenario. So, it actually represents something called the overlapping clusters. Something which I would never want is that the score is less than 0, which implies that it has been wrongly clustered, right. I would never want it. So, obviously the most favorable case could be where the Silhouette score is greater than 0, right. Now, as you can see in this particular working example that how exactly this can be calculated. So, we are evaluating, say, suppose the quality of a cluster where the k value is 2, as you can see for given data points, and these are the assignments of the clusters. So, there when some of the points belonging to cluster 1 and some of the points belonging to cluster 2, right. So, how do we calculate this score for the data point in, say, suppose A in the cluster 1, for example. So, as you can see in this particular example, so what would be step 1? So, as you can see that there are A, B, F, G, these are the 4 points which is belonging to cluster 1. So, what I am going to do is I would calculate the average distance A, as I told you, between the data point A and the other data points in cluster 1. So, as you can see I have just for an example I have taken these distances. It might be using some of the schemes, right. So, since I have not given the distances over here, so I have just assumed certain values just for the clarification part. So, for example, distance between A and B is 2, between, say, suppose A and F is 3, and between A and G is suppose 3. So, what I am going to do is I will calculate the average distance, as I told you, and that would be defined as A. So, that is what 2.67 came out to be the average distance, that is the value of A. Similarly, as you can see, I would do the step 2 where I would calculate the value of B, that is the average distance between the data point A and all other data points in the nearest neighboring, right. So, as again you can see that I would other than the cluster 1 we would now focus on cluster 2, suppose. So, A with respect to C, A with respect to D, and A with respect to E and H. So, these are all the points reflecting with the cluster 2. So, again I would be calculating the average distance, which came out to be 4.5, and then I would put them into the formula, as I can show you. this relative score becomes what? B minus of A divided by maximum of A comma B. So that would came out to be suppose 0.296. So this is how I calculate this relative score. So if you understand this, we can repeat this process for each data point in the data set, and then we can calculate the overall score by taking the average of the relative score for all the data points, right. So there is another concept which is quite popular, which is called elbow method, right, which is very important, because I have to understand that what would be the optimal value of k now. So I have understood that relative score would help us in understanding whether the clustering was good or not, but what would be the optimal value of k, right. So there has to be certain reference to it. So that is where the elbow method comes into play. So the idea is, the fundamental step for any unsupervised learning is to determine, I told you, the value of k. So elbow method does what? Where it would determine what is the optimal value of k. So as you can see now in this particular diagram, so what you can see that I have to select the value of the k as at the elbow, that is the point after which the distortion or the inertia, these two diagrams are basically represent the distortion with respect to the number of k, the k point on the x axis, similarly the inertia with respect to the k, right. So once I have this graph, so what I need is I have to look for the value of k, the point where the distortion or that inertia starts decreasing in a linear fashion. So as you can see that around the value of 3, k equal to 3, we could see a linear interpretation or linear understanding of the diagram, right. So this could be taken as one of the optimal values of k, right. So for the given particular data, as you can see, after 3 it almost follows a linear fashion. So that is how I can decide that the value of k over in this particular case could be 3, right. Now there are certain drawbacks also of the k-means. One of the drawbacks was very well understood, as I told you, that predetermining the value of k itself is something which is not feasible, right, at all the times. Another thing is that it is very sensitive to initialization of the centroids, because I took the data points randomly. So every time in every run, since the data points would be randomly selected, so as I told you, it would be non-deterministic, it would every time it is going to throw me the different results, which is not suitable in any kinds of algorithmic structure, right. And the random initialization is always not fruitful, right, because it might take lot of iterations also to actually formulate the better clusters, and sometimes it may not actually eventually fall into a better clusters, right. So if these initial cluster starts very close to each other, obviously then you would not end up anywhere, you would not be able to cluster the data points feasibly, right. So that is one of the initial drawbacks which you can see in k-means algorithm because of this randomization. So in this case, so obviously what could be the drawback, like one of the regions get over represented, another region could get completely ignored, right. So in a way the algorithm would converge into a poor solution, right, poor clustering would result in it, right. So the solution actually is hidden in something called a variation of k-means, is called k-means plus plus algorithm, where the idea, as you can see, this is a pretty good example of k-means plus plus algorithm, where how it would rectify this. So, it is a pretty good example where you can see it is a example of poor classification, poor clustering, right. So, because of this initialization of the centroids that we used to do in random fashion. So, the solution which is given by the k-means algorithm, it does what? So, it is actually nothing but it improves how the centroids are initialized in a smarter way, not the random way, right. So, that smarter initialization of the centroids, not in random fashion, actually is something which covers the overall thought process in the k-means plus plus algorithm, right. So, there can be number of ways in which we can do it, like for example, we can pick up the first centroid randomly, right. So, the first centroid can be picked up randomly, that is it, the way we were doing in the first k-means algorithm. But for the step 2, what we can do is, like for every other data point, we can compute the distance from the nearest chosen centroid, yes, and then step 3 could be like we can pick the next centroid with the probability proportional to the distance. right. In other words, in a very simple sense, I pick up the first centroid randomly, but in the second point, when I pick up the second centroid or second cluster, it should be as far as possible from the first cluster. So, I would be giving enough opportunity, and it would statistically also the possibility of since the data points are the furthest from each other, and therefore, I mean with the iterations I should be able to cover up the rest of the points in a better manner. So, that is the overall idea. So, there can be many other ways of selecting these centroids, but not randomly, and that is what the smarter initialization of the method is talked about in k-means plus plus algorithm, right. So, ultimately the points that are far away from the existing centroids have higher chance of being selected. So, that could be the concept, right, and we can repeat until the centroids whatever the number of centroids we have decided, k centroids are selected, right. Now, we will focus our attention to something called the hierarchical clustering, which is another kind of clustering technique where the hierarchical structures are present into your data. So, in that cases the hierarchical clustering could be more useful. So, it would separate your data points based on some measure of similarity, obviously, right, and finding the way to measure how they are alike and different, and further narrowing them down into the data. That is what the overall thought process that we take in hierarchical clustering. So, I mean they often reveal the finer details in a detail as we go along, right. So, they as the relationship between the data objects would be revealed in a finer steps as we go along from the bottom up fashion or in the top down fashion. So, that both the approaches that we would be discussing, right. So, they are computationally expensive first of all. So, this is one of the I would say drawback of this hierarchical clustering, and they are sensitive to noise and outliers also, right. So, there are two versions of it, as I told you. One is your agglomerative clustering, right. What it does, it merges your data points that are most similar, right, until all the points have been merged into a single cluster. So, what agglomerative clustering becomes what, in a way that you merge all your data points into the most similar until, so all the data points have been merged into a single cluster. So, initially all the data points can be thought of as what, they are independent clusters, right, every data point is independent cluster. Then we would start looking for the similarity among the data points, and as the most similar data points can be clustered, and this can be a recursive definition. And the next step, again the two most similar clusters would be grouped, and this we would continue till all the data points get clustered into a single one, right. Okay. The divisive clustering, it starts with all the points in one cluster, just the reverse part of it. So, it is absolutely a reverse of it, right, and then would we keep on splitting them. They are least similar to, based on which are least similar to each other. So, the 2 points which are least similar to each other, they would get splitted first. So, again this step can again go on in a recursive fashion till all the data points now can be broken down into single clusters, or they into the single data points, right. This is a very simple example of hierarchical clustering, which is agglomerative clustering. So, as I told you initially, on the left diagram you can see that all the data points are considered to be into independent clusters, right. So, they are presented as a scatter graph in this particular diagram. Then suppose the two nearest points, they are grouped into single group. So, this two data points, again the distance matrix would come into play. So, similarity is again proportional to the nearness of the data point, right, as it can be defined in other ways as well. So, again in the next iteration, as you can see in the last part of the graph, so the next two similar data points get clustered together, and this can continue, as you can see again. So, this process can continue till at a last stage all the data points grouped into a single cluster. So, that is what the overall thought process of the agglomerative clustering, right. So, the divisive clustering does what? So, in divisive clustering, what is happening, as you can see that we can read it from the left to right. In the same diagram could be read for the agglomerative clustering and as for the divisive clustering. So, if you are reading from left to right, it becomes your the agglomerative clustering, and if you are reading it from the right to left in this particular diagram, as you can see, it would be nothing but the divisive clustering, right. So, as you can see in this particular diagram, we can move from right to left. So, initially all the data points were into the A, B, C, D, E, F, whatever, into single group, right, and then we would see that the two farthest point would get split, right, as I told you. So, for example, one of the points got split, and this process would continue on. So, unless from right to left, you can see in the leftmost case all the data points have been grouped into a single items. So, that is how a divisive clustering talks or happens. So, while merging merging the two clusters, we check the distance between every pair of the clusters, obviously, you know, and then we merge the pair with the I would say the least distance or the most similarity, I would say, right. Now, we would also talk about something called dendrograms. As I told you, when we create this in both the top down and bottom approach, the way they are getting formulated, it was actually the dendrograms were getting developed, right. So, dendrograms is a pretty good tool to understand. It is obviously a tree like diagram, and which is used in both the hierarchical clustering to show what. So, what they are showing is, so how the data points are merging, right. So, that happens in your agglomerative clustering. If you remember that agglomerative clustering, we used to start from all the data points were into single groups, right, individually, and then we used to merge, keep on merging them till they are merged into a single group, right. At last all the data points came to a single group. So, how the data points merge? So, it would talk about this, it would, we should be able to identify by seeing that particular diagram from the dendrogram. So, this particular aspect would be covered. It would also cover, or it would also let me know that how the clusters split. So, that comes in your divisive clustering, right. So, in the divisive clustering, all the data points were into the same cluster initially. So, splitting was taking place. So, again by seeing this particular diagram, I should be able to see that how those splittings are being done. So, at every step that splitting takes place. So, by seeing this particular diagram, I should be able to see at what stage the splits were done and what data item actually got splitted up, right. And at that what distance they merge or split, that is the most important aspect. It would also let me know that at what distance they have got merged or they got split. So, this actually gives me a lot of idea about that at what stage that split and merge could be done, and many other aspects could be covered from this understanding, right. So, you can think of it as like for example, visual history of how the clusters are formulated and how they are how they got split into different clusters, right. As you can see in this particular diagram, dendrogram diagram. So, suppose you are imagining the 5 students, let us say for example A, B, C, D, E. As I have taken this, I have drawn this on the top of the right hand side diagram through certain pipes, right. So, A, B, C, D, you can think them as a something where these are the 5 students, for example, right. So, initially they are all separate, right. So, I mean this was happening in agglomerative clustering, as you can as you remember. So, when you formulate, when you run those algorithms, whether agglomerative or the divisive, actually formulating these dendrograms only. So, that is what I am telling you, right. So, initially they were all separate. So, in the step 1 what would do is, say for example, you would find that A and B are friends, for example, based on the nearness. So, obviously, I would have calculated certain distance matrix or such thing where I would have calculated distance. So, it is just for understanding point, I am taking this analogy that A and B are friends. So, they are more closer to each other. And similarly, in the same step you can see that again the D and E are also friends. So, they got merged together, right. As you can see, we started calling them as a new group or a new merging group, which is called AB, and similarly the next group would be the DE, for example, in this diagram, as you can see. The step 2, like for example, next stage. So, we are coming down from top to down, as you can see, right. So, initially all the data points were separate. So, now again we saw that both A and B also joined together, right. So, they got joined. So, we have joined A and B, and step 3, that the 2 big groups got merged together at the last, right. So, as you can see, what does this dendrogram is showing if I want to understand? So, to two important aspects they are able to cover. One is the order of merging. So, which data points merge first, that was clearly understood from that diagram, right. Then the which merge later, which group merge later, right. Earlier merge means more similar, right, and later merging means less similar. So, this thought process is very important for me, right. Another aspect which it would cover is what? The distance between the clusters, that is the height of the merge indicates your distance, for example, right. For example, the x axis, as you can see in the previous, it was the data point, and y axis was the distance, that is dissimilarity, right. So, the lower height means very similar, and the higher height means what? Very different. So, that is what. So, how you can use it, that is the purpose we must understand. So, for choosing the number of the clusters, I mean if at any point of time I have to use the number of clusters, we draw a horizontal line across the dendrogram, right, and whenever that line cuts the branches, the number of vertical line it crosses is nothing but the number of clusters, as you can see in this particular case, right. So, I have given different cuts. So, at case 1 I have done a cut at a higher level, where we draw a horizontal line at suppose height 6. So, in this particular case it left the group into one cluster only, that is A, B, C, D, E, right. So, if we cut on a very high, everything belongs to into one group, right. So, vertical axis means again I told you it is a distance, and the horizontal axis here is the data points. Similarly, I have chosen and shown you that a case 2 where the cut is done at a middle stage, right, at a value of suppose 4.5 in the particular diagram, as you can see. So, obviously, it has led to what? Two clusters, as you can see at the bottom, that A, B, C, another cluster got formulated as D and D, right. I have used another cluster, I mean cut, which is at a point, say suppose 3.2, as you can see the clusters formulated now, more number of clusters got generated. So, at I have tried it case 4 also, where I made a cluster, I mean did a cut at another point, as you can see in particular case, which resulted in what? Further more number of clusters. So, whenever you draw a horizontal line, the number of vertical branches it cuts equals the number of clusters. That is the concept that you must know. So, one thing you must always note, where at times the students have a wrong understanding about this, a dendrogram does not tell you how many clusters to choose. Remember always that. It only shows you all possible clusterings, and you just decide where to cut, right. So, you look for the large vertical gaps, big jumps in height, and the natural separation. So, that is what you can do it, right, and stability before big merges, right. So, larger jump means over here the clusters being merged were very different, okay. So, that is the end for today's session, and thank you everyone.